Welcome to the NERI SimCenter's Live Expert Tips. In this session, we introduce you to Bayesian calibration. We do this with an example of a reduced order model in OpenSees to approximate the nonlinear response of a 9-story steel structure. The calibrated reduced order model can then be used for further uncertainty quantification analysis. The calibrated model is used for seismic risk assessment utilizing synthetic ground motions with the SimCenter's EEUQ application. Our expert today is Dr. Aakash, Bangalore, Satish. He is a postdoctoral researcher at UC Berkeley with the NERI SimCenter and a lead developer of the quoFEM application. Aakash received his PhD from the Department of Civil and Systems Engineering at Johns Hopkins University. His research interests include Bayesian estimation and model selection and averaging. Aakash, thank you for being here.
Thank you very much, Matt. Thank you for the introduction of the topic. So I think I'll just dive right in. So the SimCenter is part of the research infrastructure funded by NSF through the NIHIRI program to advance the capabilities to simulate the impact of natural hazard events on infrastructure and communities. The center releases desktop applications that have been built utilizing an open source framework developed by the SimCenter to support computational modeling and simulation in natural hazards engineering. The released applications are all free and open source, and they consist of a front-end user interface and a backend, which drives the analysis. For example, the quoFEM application consists of the uncertainty quantification or the UQ component and the cloud computing component of our backend. The cloud computing component makes running large numbers of complex simulations feasible. Other applications for response estimation, like the EEUQ application, build on the features in quoFEM, while also incorporating features to help build structural models and define the hazard loads and evaluate the response. PBE builds on the response estimation tools and enables performance assessment, and R2D uses all the components in our framework to enable regional simulation. In this session, I will give an overview of the methods available through the UQ component and in the quoFEM tool. Then I will present an example which uses the Bayesian calibration capability enabled by quoFEM, and then uses the EEUQ application for seismic risk assessment with the calibrated model. Now, just a brief overview of the features of quoFEM. The quoFEM application is developed to advance the use of uncertainty quantification and optimization within the field of natural hazards engineering. The acronym quoFEM stands for Quantified Uncertainty and Optimization for the Finite Element Method. Before using quoFEM, the user would need to first develop the computational model outside of quoFEM that they want to use in their UQ analysis. Once they have such a computational model, the tool will then enable the user to plug in their models into UQ algorithms implemented in the backend. There are algorithms that enable the user to solve both forward problems as well as inverse problems. Forward problems such as uncertainty propagation or conducting sensitivity analysis or reliability analysis. Now, in addition to the computational model, in order to solve inverse problems, the user would also need to provide data that would be used to calibrate the models. In the data could be, for example, obtained from experiments, or as is the case in today's example, in today's exercise, the data used for calibration was obtained by using an expensive finite element model. And conducting such kind of UQ analysis needs the computational model to be evaluated a large number of times. So if there are cheap models that can approximate the response of the expensive models, they can accelerate the UQ analysis and enable doing UQ for more problems. So quoFEM also has modules which help develop such surrogate models or such cheaper to evaluate approximations of the high computational cost models. This page shows a list of all the UQ algorithms that are supported in quoFEM. And quoFEM then allows the user to plug in their user-developed, user-defined computational models, which are scripts that could be written, for example, in OpenSees or in Python or in other software. Before getting into the details of today's example, I would like to point out some resources that you can use. So these are links to the web pages of the two tools that we will be using in today's example. So here you will, if you navigate to these, to the web pages of these tools, you will find links to where you can download these applications. You'll find links to the documentation, which contain instructions on how to install and use our software tools. And there are also examples that demonstrate the use of the features of the tools. You will also find links to previous live expert tip session recordings and tool training videos to get introduced to the features of the tools in detail. I'm also pointing to the GitHub page. So all of our software developments are open source. So you can take a look at our GitHub page and you'll find all the source code for all our repositories over there. So if you're interested in building the application from source, or if you want to tweak the workflow to your needs, or you want to contribute new features, so you can take a look at our GitHub page to find details of that. And if you have any questions about running the tools, or if you encounter any problems, or if you want to request new features that can be added to the tools, then you can please make use of our SimCenter forum, where you can post the details, and we will respond to the forum postings pretty we try to respond to all our forum postings within a 24-hour time period. And if you want to use our tools, all our tools enable running the analysis on the cloud computing, on the high performance computing capabilities provided by DesignSafe. So in order to be able to run those analysis on DesignSafe's computers, you would need to get a DesignSafe account. And this is the link that you can use to register for a DesignSafe account. Now here is just an overview of the example problem that we'll be going through today. So using high-fidelity finite element models to describe the nonlinear response history of structures in probabilistic analyses incurs very high computational cost. Reduced order models can be used to cheaply approximate the response of the high-fidelity models. And the calibrated reduced order models can then be leveraged in probabilistic analyses to reduce the computational burden in running the UK analyses. So in this session, the steps needed to perform Bayesian calibration in quoFEM will be demonstrated using an example. The example walks through Bayesian calibration of a reduced order model in OpenSees for approximating the nonlinear response of a finite element model of a 9-story steel structure. So I just want to emphasize, we want to calibrate the parameters of the reduced order model such that not only the linear response, but also the nonlinear response is matched well. And then the calibrated reduced order model can be used for further UQ analysis. As an example, the calibrated model will be used for seismic risk assessment employing synthetic ground motions within the SimCenter's EEUQ tool. As I mentioned previously, before we can perform Bayesian calibration in quoFEM, we need to prepare two things: the computational model, whose parameters we want to calibrate, and the data that will be used for calibration. So I'll now first talk about the model that we will use in this example. In this case, we want to approximate the nonlinear response of a 9-story steel moment frame structure, which is modeled in OpenSees. We are interested only in the response at the rightmost column line of that structure at the floor levels. So we are only interested in approximating the nonlinear response time history at these 9 degrees of freedom in that model. So to do this, we first perform static condensation and obtain the 9x9 stiffness matrix that corresponds to 9 degrees of freedom that we are interested in. We will then build another model in OpenSees, which will serve as our approximate model, as the model that we use for approximating the response from this high-fidelity model. So we will follow the choice of the reduced order model that was used in the reference shown on this slide. The reduced order model is a 9 degree of freedom lumped mass model, where every degree of freedom is connected to every other degree of freedom in the model by springs. The elastic stiffness of these springs are set to the corresponding values in the 9 by 9 stiffness matrix obtained by static condensation of the high fidelity model. So by doing this, the reduced order model can exactly reproduce the linear response of the high fidelity finite element model. Now, in order to also match the nonlinear response well, we will replace the 9 springs that connect adjacent degrees of freedom by nonlinear springs, which have a quoFEM material model. So the parameters governing the elastic response of these springs are still the same as before, but there are 4 additional parameters per spring that govern the nonlinear response of each of these springs. So these are the parameters that we will calibrate using data generated from the high fidelity model. So there are a total of 36 parameters that need to be calibrated. And we will next see how we get the data that will be used for calibration. Calibration can be done to match the desired characteristics of the high fidelity model. So these can be multiple output quantities of interest. In this problem, the time history of the interstory drift response of the high fidelity model is used in calibration. Since our objective is to match the nonlinear response time history, the inputs used are earthquake ground motions that elicit nonlinear structural response. The specific ground motions that we would use and the number of the ground motions that you want to use should be carefully selected based on the requirements of the analysis that you are interested in. In this example, the 3 ground motions that are shown on the slide were used to generate the data. The selected ground motions cause a significant nonlinear response in this high fidelity model. So the high fidelity model was subjected to these 3 ground motions, and the interstory drift ratios was recorded. So this shows an example of the time history of the interstory drift ratio for floor 1, coming from the 3 different earthquake ground motions that were applied to the structure. But as we can observe, only a portion of the ground motions corresponds to periods of strong shaking where the structure behaves non-linearly. So only that data would be useful for calibration. So we don't need to use all of the other data because we are already using elastic spring parameters that match the linear response exactly. So we would only want to obtain data correspond where the response is nonlinear. So to do that, we obtain the time that corresponds to periods of strong shaking in these ground motions. And that is done by choosing 10 to 95% of the cumulative areas in intensity. And within that time period, a discretization interval of 0.05 seconds is chosen to obtain the data for calibration. And the data corresponds to the interstory drift of all the 9 stories. So to wrap up or to summarize, so the calibration data that we'll be using is the interstory drift ratio of all of these 9 stories during the time of strong shaking taken at an interval of 0.05 seconds. And then now we have all our ingredients ready and we can now perform calibration. Doing Bayesian calibration allows identification of the entire posterior distribution of the reduced order model parameters. So this quantifies the uncertainty in the calibrated parameter values of the reduced order model. And this uncertainty can also be propagated through any forward analysis for making more robust predictions. So I'll now just give a brief demo of how we can run the 2 analyses that I mentioned. All the files that are used in the demo are available at this location. I'll now switch to quoFEM and switch to my file system just for a minute. So if you download the files that are shared on that directory on Google Drive, then you will get this file structure. So there will be 2 folders. one of which corresponds to running the forward propagation or running the Bayesian calibration in quoFEM, and the other folder contains all the scripts, all the files that you would need to perform the forward propagation in EUQ after doing Bayesian calibration in quoFEM. So if I now just take a look in one of these directories, so these are all the files that we will be using as part of the Bayesian calibration. So I just outlined how the calibration data was prepared. So the calibration data is saved in a text file. Since there is only, so the way to store the calibration data is in a single line, in a single row. So here there is a single row which contains all the inter-story drift ratios of the 9 stories across the 3 different earthquakes. So that was the calibration data, and we also prepared a model script of the reduced order model that is in this file shown. So here there are 36 parameters that need to be calibrated, and the way to let quoFEM know that some parameters in your model are random variables is by using the pset keyword instead of the set keyword. So here you will see the 36 parameters which correspond to the 4 parameters governing the nonlinear response of each of the 9 springs. And if you observe this, if you look into this script performs one deterministic analysis. So given a particular value of the parameters of your model, this script runs one analysis, and it produces a lot of output files, which are saved in these files. So these are the output files that are created when you run the model. But quoFEM requires all the outputs to be written to a file called results.out. And as I also mentioned, once we have all of the data, we are not using all of the data for calibration. So we only need the data that corresponds to the period of strong shaking. And we are also using a sampling frequency of 0.05 seconds. So once we have the response of the inter-story drift history, there is this post-processing script, which then prepares a file known as results.out, which contains only the output that is used during the calibration process. So that was an overview of the files of the model and the data. Now there is also a file in this directory called inputs.json. So this is a JSON file that contains all the information that I have previously prepared that you can load into quoFEM. So now when you open quoFEM, you can then open in JSON files using quoFEM. So if you now select the inputs.json file, it is automatically going to populate all the panels with all the required fields, with all the required entries in all the fields that will let you run the Bayesian calibration analysis. So here I'm requesting 500 samples from the posterior, and I'm using the transitional Markov chain Monte Carlo algorithm to perform the Bayesian calibration. So I can give a seed that will ensure reproducibility across several runs. And all the calibration data that I'm using is saved in this file, which was called calibration data.txt. And on the FEM panel, we enter the name of the main input script that contains the pset keyword and the post-process script. And in the RV panel, this shows the list of the 36 input parameters that we are calibrating. And these are the prior probability distributions that are being used in this Bayesian calibration. And in the EDP panel, so there is a total length of 5,670. So this is the length of the calibration data file that we are using in this example. And you can, in order to run this analysis, you can log into design safe And if you click run at design safe, it will perform the calibration remotely by using the HPC resources at design safe. Or if you click the run button, it will do the Bayesian calibration locally on your machine. So this is how you can perform Bayesian calibration. So in the end, the results panel will be populated with the results of your analysis. Once you have those results, you can then compute. We show what is the posterior mean value of all the parameter estimates. And I will now move on to the second part of the example, which is doing forward propagation using the calibrated model parameters in EEUQ. Now, again, if you go back to the same directory, you will find the files that will let you run forward propagation analysis using EEUQ. So there is a JSON file, which I will now open using EEUQ, which will populate all the fields required. To reproduce the analysis. So after loading the file, you will see that the finite element model, that is the simulation model, what is the simulation model being that is going to be used. And you will also, to do the forward propagation, we'll be using synthetically generated ground motions. So that is done in the event panel here. This generates synthetic ground motions corresponding to a scenario where the moment magnitude is 7.5, the rupture distance is 20, and the shear wave velocity for the top 30 meters is 600. And here again, you can provide a seed value, which will ensure that you can reproduce the forward propagation results also if you run it again. And these are the analysis options in OpenSees. And in this case, I'm only choosing to run at the posterior mean value of the parameters that were calibrated in quoFEM. So I don't have any other random variables. But you could also choose to propagate all the uncertainty in the posterior parameter estimates, in which case you would have 36 random variables, which would be the parameters that we just did Bayesian calibration of. Now, again, so you can choose to run it either at design safe, or you can run this locally. So this is how you can run the analysis using all the files that were shared with you. Now, quickly coming back to my presentation, I'll just show a sample of the kind of results that you would get if you run these analyses. So first, I'm going to show the results of the calibration exercise. So we subjected the models to 3 ground motions. So here we see that the original higher fidelity finite element model took about 5 minutes to do the analysis on my machine, whereas the reduced order model that we used can do the analysis within a period of about 3 seconds. So this reduced order model is about 100 times faster than the original model. So, so this is a cheap approximation of this model, but is it any good? So in order to see that, we can look at the results on the right-hand portion of the slide. So we see that there are 3 lines on each of these 3 figures. So the 3 figures correspond to the 3 different earthquake ground motions that were used. And I'm just showing a sample of the results after calibration. So this is showing the inter-story drift ratio for story 1. The blue line here is the prediction that is coming from the high-fidelity model high-fidelity model. So this was the data that was used for calibration. The green line here is a linear reduced order model. So that is if we don't have the quoFEM model, if we don't have the nonlinear springs. So this is what would be predicted by the linear reduced order model. But now after doing the calibration of the nonlinear model parameters, we see that the response of this calibrated model, which is shown here in red, matches quite well with what is the output from the high fidelity model. So now we have, after doing this calibration, we have a cheap approximation, which is also pretty accurate. And as it is, after doing the Bayesian calibration, you will get these posterior samples drawn from the posterior probability distribution. So instead of just using the posterior mean, you can also propagate the uncertainty in these parameter values, and you will end up getting a band around the predictions of the reduced order model. So that is the kind of result you get from the Bayesian calibration. Now coming to the seismic risk assessment. So in this case, I used the calibrated reduced order model, and I generated 200 artificial ground motions, synthetic ground motions corresponding to this scenario. And in the end, so EEUQ lets you automatically obtain standard engineering demand parameters that are used widely in seismic risk assessment. So such as the peak interstory drift or the peak floor acceleration. So here I'm showing what is the probability of exceedance of these demand parameters. So because there is uncertainty in the ground motion corresponding to this event, so there are 200 ground motions which lead to 200 different predictions of the peak interstory drift or the peak floor acceleration. So this shows the probability of exceedance of different threshold values of these peak interstory drift or the peak floor acceleration. The results from the reduced order model are what is shown on this red curve. Now, just as a validation exercise, I ran the same analysis by setting the seed. So I have the same set of ground motions using the original, the higher fidelity finite element model. And I also computed the same curve for that model. And the results are shown in the red line here. So we see that even though I only used 3 ground motions to calibrate the reduced order model, and I now subjected that model to 200 new ground motions that were not part of the calibration process, the predictions, and also I'm predicting quantities here that were not part of the calibration, that were not used in calibration. I did not use any acceleration values. And I did not try to match only the peak interstory drift. I actually tried to match the entirety of the interstory drift history. But still, the peak values are also matching pretty reasonably well. And the peak floor accelerations are also matching reasonably well for all the 200 ground motions that were part of the risk assessment. So this is a validation exercise, which shows that the calibration that we did is the model is able to even generalized to other scenarios. But you need to be careful. So you have to use the right set of ground motions while doing the calibration so that they don't cause even larger peak interstory drift. So if you have not used that in calibration, you'll not be able to get good results in the validation exercise. So that brings me to an end of the presentation. And here are some upcoming features of quoFEM. So we plan to implement model class, Bayesian model class selection and averaging, and multi-fidelity Monte Carlo. So here we saw an example where we calibrated a lower fidelity model. But by doing so, we are not always guaranteed accuracy, but the multi-fidelity methods enable us to also use the higher fidelity model, but use much more evaluations of the low fidelity model to guarantee accuracy as well as high precision in estimates of the statistics of interest. And we also will have surrogate aided Bayesian model updating, which will help us deal with more expensive models, computational models. I also would like to point out that we have UQ office hours every Friday at noon, and you can check our SimCenter forum for that announcement. And if you have any questions about today's talk, so you can always reach out to us on the SimCenter forum. So that brings me to an end of the presentation. Thank you very much.
Aakash, thank you very much for this example, for the presentation, and stepping through that those exercises of how to put those pieces together, from calibrating a model to calibrating a model, a reduced order model, and then working through how it would be then used in EEUQ to further explore ground motions beyond those that were used in the calibration process. Very, very interesting. So thank you very much. To the attendees, thank you for being here. We are at the end of our session today, so I want to just say thank you one more time for for those attendees in the room, as well as to Aakash for the presentation. If you would like to join other live expert tips, I encourage you to join, look at the SimCenter website, which is simcenter.designsafe-ci.org, where you can find other upcoming events, including things like our live expert tips. So this concludes today's session. Thank you very much for joining.
Thank you.